Hello, and welcome to my talk on basically an introduction to C as a programming language, a couple of concepts around it, as just a bit of a primer for learning the language in full. This is recorded as kind of a supplement to the in-person one that I did around about a week ago. So hopefully we'll be able to cover the same things, and there won't be any errors in the slides, which should have been corrected since last time. C was designed Bell Labs, 1970s, as a successor language to B, which was intended to be used to rewrite the Unix kernel, which is what Linux is based on, and also Mac OS. Because of this, C is a very low-level language. When we talk about levels of abstraction in programming languages, it's a very relative term. C is high-level compared to assembly, but low-level compared to most of the languages you're probably used to working with, things like Python and Java and JavaScript. Basically, one of the main hallmarks of low-level languages is that they generally compile down to machine code rather than being interpreted by an external program, in the case of Java with its JVM and bytecode, and in the case of Python, interpreted line by line. C is also statically typed, meaning that the types of all variables are determined at runtime and checked with the compiler. This is really important for, one, memory layout things, and also correctness. And there's a lot of correctness is very important in C, as we'll come to learn about later. And also manual memory management, very big thing. Being able to talk about the cells of memory, whether we're passing a copy of an object or a pointer to it. We'll get to that again later in this talk, which will be good. And controlling whether things are allocated or deallocated, which is very, very important for writing both efficient programs and programs that do the things that we intend them to do. We're going to cover a couple of things today, mostly the syntax of C, a very base level overview of that, pointers, which is the main difference that you'll be encountering with C compared to the higher level programming languages, which either abstract away pointers or have them as a implementation detail that you only run into when you start encountering problems. And some of the mistakes that you can make in C and what happens when that occurs. Obviously, we're not going to be talking too much about a lot of the stuff for 2010 today. C for AVR. AVR being the architecture of the microcontrollers that we're working with. It's very hard to show examples for stuff that occurs on embedded chips without obviously having one on hand. And it's much easier to write programs in user land where we can obviously see the output of things being printed to the console. We're also not going to touch on microcontrollers a lot. We will talk a little bit about some of the changes that happen between userland and microcontrollers, but it won't be too much, and this talk is definitely not on them in specific. Right, for this talk, we're obviously going to be running a couple of examples, doing some exercises, and to do that, you're going to need a couple of tools installed. The code for all of this is provided on Foxhaven Git. This includes layouts for exercises, the code for my examples, solutions for those exercises, a bit of a reference, as well as a couple of other things that will be useful to your learning. It also contains handouts, which are just these slides without my click-through animations. Obviously, just download that as a zip and unzip it into local directory. There are instructions in the README if you need. We are going to be running stuff in the terminal. Unfortunately, I don't want anyone installing a fully fledged IDE for this, mainly because it makes my life harder to do cross-platform things, so we'll just be doing things in the terminal. These are instructions on how to get set up in Windows Terminal. In practice, I recommend using VS Code or some other editor that allows you to launch a terminal in your project directory. It's going to make your life easier and allow you to edit things and run a lot quicker. So that's going to be very beneficial. Because C is statically compiled, we need a compiler to turn our source files into binaries that we can actually run. We can't just run a C program on its own. We're going to be using Zig for our C compiler. There's a couple of other ones like LLVM's Clang or Windows's MSVC. Problem with MSVC is that it's a huge pain in the ass to get working, especially from the command line. And in this case, it also doesn't work on macOS. Zig is based around Clang, but has a lot of nicer features for cross-compilation. So it mostly makes my job easier to do it. You can install it either through winget or Homebrew if you're on Mac. Obviously, look up instructions on how to install Homebrew if you haven't before. This is a basic overview of how we compile a C file into an executable that we can run. There's obviously quite a few things that I don't include for this, and this is not all the compiler flags that you can use for Zig or a C compiler in general. It's fairly consistent across things like GCC and Clang. Very standard interface. MSVC is a weird one. You won't need to be invoking this command directly because we'll be using just to run tasks. The repository contains a just file, which basically contains all the commands that we'll be running for various examples, the exercises, and things like that. Once you've got all of those installed, you'll need to restart your terminal. If you're using VS Code, you'll need to close out of the program fully in order to have your path restart. If you're still running into issues with getting things available, try restarting your computer or reinstalling the applications again. Sometimes that fixes it. To double check that things are right, run just --list. That'll show all of the commands. If you want to check that Zig's installed, I recommend running zig zen in order to just check that it's installed. And you'll need to run just init to set up build directories for various things. That's just so that Zig knows where to put your files after we build things. Right, now that we have got that sorted, it's time to talk about the simple bit, syntax. C is basically the lingua franca of programming languages, and so a lot of them steal syntax features from C. So if you know another programming language like Java, your life is going to be quite easy, and C syntax will be very familiar. But we will still go over it from the top. To start off with, data types are something that we care a lot about in C because they allow us to declare things of different sizes and allow the type checker to make sure that values are compatible with the functions we're applying to them. The sizes I have written here based on the AMD 64 or x86 64 architecture. C is a language that's defined for many, many CPU architectures, and because of that, char, short, int long, and long long often have different sizes or may not be available depending on the kind of architecture that you're working with. Int is kind of meant to be the platform's native integer size. It's still 32-bit on 64-bit systems because we had 32-bit systems for so long that we ended up just needing to carry that across into 64-bit C because it would break a ton of code otherwise, and in this case it actually provides some nice backwards compatibility. Our integers by default are signed on AMD64. This is using 2's comp. In practice, it doesn't matter because we're never manipulating the binary streams directly. But we can also set them to unsigned, which is, again, fairly normal. Bool, or booleans, don't actually exist natively in C. We need a library to supply that, and it's more or less just an alias for whatever that platform's 8-bit type is, where true is 1 and false is 0, like on most platforms. We'll get to some caveats around Bool's representation later. In practice, if I'm writing actual C code and not just generating examples for a talk, I'll be using stuff from standard int, which sorts integers by their size and signedness rather than the kind of vague descriptors we get with int long and char and things like that. It just helps with other people who are reading your code, and also has benefits when building across platforms. The include directives just copy some code from a library into your C file. Pointers are very prevalent in C, and we aren't able to discuss strings and arrays until we talk about those, so that will be later. Assignment in C, very similar to the way that you would see it done in Java, where you declare a variable with a type and a value. You can also just declare a variable without a value and initialize it later. In practice, we don't do that a ton. For Boolean logic, it's very standard. Double ampersands for and, double bars for or, and the exclamation mark for not. One thing to remind people is that I've got ligatures set up for this. If you've used a language like Python or Java or literally any other language with comparison operators, these are all the same things. I just have ligatures on because it's clearer. I probably should take it off, but I'm not going to. Anyway, conditions in C, very standard. If, else if, else. For C's switch statements, we don't really have a constructor like Java where we can assign out of a switch. It's all imperative and is just a nicer way of writing if chains. The break at the end of each case is not necessary, but it does help with performance by more or less short-circuiting that control structure so that we don't check any of the cases below it. So if something passes the test for X, we won't bother checking if it passes the test for Y, and so on. Some cases we might want to assign a value to something based on a condition. Delayed initialization is one way we can do that, but we also have the ternary operator, which allows us to turn an if statement into an expression rather than a regular control flow item. So we can assign this directly to a value, or we can pass it to a function, which is very useful for writing more concise code. Iteration has two main constructs that we'll talk about: the while loop, which is very common in other languages, and also the do while loop. The difference between these is that while checks the condition before doing the inner code, whilst do while checks it after. So if you have a block of code that is within a do while statement, it will always run at least once. In practice, it's not super useful, but it's something to be aware of if you're reading other people's code. There's also, of course, the classic for loop. C doesn't have iterator syntax, so there's no real way to write for I in array or like for I in range. You only have access to the standard for loop construct of initialize some starting value, have a condition that's checked at the end of the loop, and perform some operation that changes that state. In practice, this just desugars to a while loop within the compiler. Very, very standard for languages. Functions in C are very similar, again, to functions in Java, because Java cribs a lot of its design from C. In this case, we have to declare both the type of the inputs and the type of the output. In the case of languages like Python, typing annotations aren't entirely necessary, because typing in Python is actually just a mess. But, of course, but we declare a function with its inputs typed. We declare a function by stating the functions have to be specified with types for both its inputs and its output, mostly so that the type checker can make sure that you're passing the correct kind of values to functions. This prevents a lot of errors that languages like Python would have to track at compile time, and just makes your life a lot easier. Function call syntax, again, very standard. You pass the values within the parentheses, comma separating the arguments. For our Hello World program, it's a little bit more complicated than Python's one-liner, because C is low level enough that we don't actually have native print operations. In this case, we need to import a library which will call out to system functionality in order to print some text to our terminal. Our return value from int main is the exit code of the application. Under most systems, 0 means success. Any other value generally means that something went wrong, which is a good way to check if a process has succeeded in what it's doing. And C forces us to declare that directly. Printf also doesn't automatically insert a new line, so we have to use escape syntax to write a new line at the end of Hello World. If you want to try this example, you'll need to open up your terminal in the project directory, and after running just init to set up your builds directories, run -example hello, which will compile examples hello.c and run it. Printf also allows you to do format strings, which allows you to insert the contents of variables into your output. without needing to deliberately turn them into strings with functions. This is how we tend to output values. We use %d for integers and anything that's similar to an integer. So if you're passing a short or a long long, that works as well. %c interprets a character as a, I believe, UTF-8 character and prints it to the screen. So you can pass a char to %d as long as you're using it as a integer output. %f is also for floating point types, which have a different kind of structure to integers. And we'll get to %s for strings a little bit later, how that works with our general code. Again, if you would like to run this example, you can use just to run printf. All of that code is under the examples directory. Right, let's talk about pointers now. A little bit of a note before we go into this. The model I'm about to present to you is a lie, in a sense. Memory models are really a tower of weakenings where we're able to introduce or remove details depending on what we need to know about a system. So things are inherently more complicated under the hood. In practice, it's really easy to teach this model that I'm presenting today. It's deliberately more restrictive. There are going to be certain things that you can't do within it, but because of that restriction, you're going to make less mistakes when writing code, which is one of the things that kind of puts people off languages with pointers, because there are a lot of ways you can screw up, as we will find later. To talk about pointers, we're just going to do more or less a very simple definition of memory. We'll treat memory like a big tape of cells. When I show this visualization on the screen, I'm showing a slice of that tape. In practice, it's not contiguous. In practice, it's not infinite. And initialization isn't real. But we will treat it as if it is, because it will work well for our mental model. In this case, I've allocated two local variables, x and y, and I've placed them into the tape. A note about variables in C that has a major difference to the way that variables operate in Python and Java that will have some implications for later. Variables are dropped at the end of their scope. In this case, I'm just using if true to create a scope that always executes. At the start, we allocate our variables x and y and assign them their values. Then we go into our inner scope. We assign something to z and we use its value to update x. And then once we're outside of that scope, z is removed from the tape. There's no way that we can access it. There's no way for us to read from it. We can't write x plus equals z outside of that scope, because to see, it no longer exists. Arrays are more or less big collections of cells. Each item of an array you should think of as having its own cell, and then an array spanning over that cell, over all of those cells, as kind of a marker of that. In this case, we're using set notation to assign values to it. Now, arrays are fixed length, meaning that we can't just add more elements to it than we've allocated space for. In this case, we've allocated space for 8 cells. When we declare, using set notation, the contents of an array that is less than the length of the array, C will initialize all of the values to some kind of sentinel value that makes sense for that type. In the case of numbers and things like that, it's mostly just 0. In the case of a Boolean, it would probably be false, because that's how it's represented as bits. Size of allows us to return, ironically, the size of a value in bytes. And this is something that has to be determined at compile time. So, in order to find the number of elements in an array, we're able to take the size of the full buffer in bytes and divide it by the size of the first element in bytes, because arrays in C are homogeneous. Every element in an array is of the same size, and they are a fixed length. Now, this method wouldn't actually work if we were passing an array into a function, because the function doesn't know the size of the input without directly inlining it. There's no way to use size of to determine the number of elements in an array that we pass to a function, but because array is known at compile time and it's in our scope, we're able to perform this trick. If you'd like to run this example, it should be sum underscore array. C doesn't have a built-in string type. Instead, we use a list of 8-bit characters that are terminated with a special character called null. The length of this string without the null character can be determined using a function from the string library in C. And just to show that arrays and strings are the same thing, here are the 2 ways that we can initialize it. Now, we need that null byte at the end, because in a lot of cases, we're passing strings that aren't going to have a compile time known length, and a lot of the operations we're doing with strings are often performed in the context of using pointers instead of a statically allocated array that we're passing around. Which brings us to pointers. Sometimes we want to be able to pass a variable to a function without creating a copy, or other times we want to allow a function to mutate something that we have in our context. We want to be able to pass it in and let it make changes and see those changes reflected in our scope. Pointers are more or less magic arrows that make this possible. The ampersand creates a pointer to a place. A place is just a fancy word for variable name to kind of distinguish between the value at X and the name X itself. It's a bit of useful terminology that often pops up when we're talking about this theoretically. If we create a pointer to a place with type T, it will create a item of type T pointer. In this case, we create 2 variables, and then we create another that is a pointer to X. We can also undo this operation and turn a pointer back into the type that it points to. In this case, we're taking a reference to X, and then we're dereferencing it using a unary asterisk. This is different from the multiplication operator and has a higher precedence to bind to variable names. And it basically just allows us to copy out the value behind x and use it in another context. In this case, we initialize y by adding 28 to it. In practice, arrays are actually just syntactic sugar over pointers. Once the C compiler has allocated the buffer for all of the items in the array, we're working in pointer land. So the syntax that we use for referencing elements of an array actually is just taking the pointer to the array, adding I. In this case, when we add a number to a pointer, in address space, we're actually adding the number of bytes that is the size of each element. So it just allows us to make sure that array 0 and array 1 are disjoint items in memory, which prevents us from causing problems. In this case, the array square bracket syntax allows us to also dereference this, so it will do a copy out. If we want to create a reference to an element, we need to just put the ampersand in front of it to tell C that we want a reference instead of a copy. We can also use pointer arithmetic in a similar way to do a sum example like we did before with our known size. In this case, we need to specify the length as an input to the function. Because we don't know the size of the array, there's no way that we can know this at compile time just from the pointer. So we need to have the user of the function pass it, and it's a bit of correctness that they're going to have to be determining. We're able to just add 1 each time, as we do with the normal setup, but instead of adding 1 in address space, it's actually adding size of int in address space and then dereferencing each element and adding them together. Again, you should be able to run this example using just. Another thing to keep an eye out of when using 2 pointers of the same type is something called mutable aliasing. In this case, we would like to assume, say we're a formal verifier program that wants to ensure that the values stored at P and Q are 2 greater than they previously were. But thanks to mutable aliasing, that's actually not true, because we could pass the same pointer twice. So we would do 0 plus 2 and then assign 2. And then we would perform 2 plus 2 and assign 4. And now both P and Q are 4 greater than they previously were instead of 2. This is obviously quite an issue, and it's one of the things that can really throw people, passing the same reference twice and updating a value. This is what models like separation logic and language features like Rust's distinction between shared XOR mutable is designed to solve, so that you can know in the syntax or at compile time or when you're doing analysis whether 2 pointers will ever point to the same location, which turns out is a very useful thing to be able to know. Right, since we can perform pointer arithmetic on any pointer, it doesn't have to be arrays. We can do this to any pointer. Here is a theoretical question. What the fuck does x plus 1 point to? I'm gonna do another take of that. Here's an interesting question. What does x plus 1 point to? In this case, ref is just a pointer to X, a single cell in memory. If we add 1 to this, well, we're adding size of int, so we're shifting things over in the address space. So it could be the variable y. I've very deliberately set up this example to make x and y the same size. But in a practical example, we can't always assume this, and there might actually be some padding in the address space between x and y. There's no guarantees about where things are going to sit. Because of this, we need to give pointers a property called provenance. Provenance is a very useful tool, and basically what it says is that a pointer belongs to an allocation, or a pointer is an offset into some sort of allocation. That could be a variable, it could be an array, or it can be some memory that we allocate ourselves using system functions on an external structure called the heap. In practice, x plus 1 is undefined. We have no way to tell what it is because it's not within x's allocation. It could be y, but it also couldn't, and there's no way for us to really know that in a way that's deterministic. So because of this, we can have our reference to x treat y like it's essentially invisible because it doesn't belong to the same allocation. In this case, I'm coloring the arrows based on what allocation they belong to as kind of a visual aid to show this off. We can do a very similar thing for arrays. With arrays, as I've shown earlier, they have an allocation that spans multiple cells, and this is why it's sound for us to do x plus 1 to access another element of an array, but not to perform x plus 1 to access another variable in the scope. In this case, ref2 is perfectly fine. It's within the bounds of the array. If we were to dereference this, we know that we will get 16. With ref3, we're outside of the array, so we don't know what that value could be. We just treat it as undefined. Ref4 is just x, and of course we can't step backwards into arrays allocation because to us that doesn't exist. It's an operation that is fundamentally nonsense. A note on provenance is that there's a couple of different models that we use for it. The model we're teaching here is strict provenance, where every pointer has meaning and you can't just create a pointer to the same address and expect it to have the same provenance as a pointer that was created from that allocation. There's also exposed provenance, where you can pick up an allocation by virtue of having the same address as the cell, or like, it's a bit messy and it kind of sucks, which is why most people doing formal methods or building this kind of stuff don't like it. It's not as useful a model. The only thing that kind of falls in exposed provenance's favor is to do with microcontrollers. In a lot of cases, when dealing with things like Arduinos, you're performing memory mapped I/O, where you write to a specific address, and that turns a light on, or you read from a specific address, and that's the amount of electricity flowing through a certain pin on the board, which is quite useful. In that case, we'd say that those pointers do have provenance. They belong to an allocation, but that provenance and that allocation is defined by the architecture rather than the language and our code. It's a bit messy, but it kind of unifies this much tighter model with the complexities of low-level hardware and is useful to keep in mind. Dangling pointers. Of course, when we combined pointers with our scoping rules, there is inevitably reasons where things can go wrong. In this case, we've set up the tape with two variables. We've initialized x to something, and we've created an uninitialized cell and given it the name y. So we're going to assign it a value later. When we go into the scope, we'll create a new variable called z, and we'll assign a reference to it to y. Now, once we exit the scope that we've created, that little if true, z no longer exists in our tape. C has gotten rid of it because it drops variables at the end of the scope. So y is now an invalid pointer because it's not touching an allocation. This is slightly different to exceeding the bounds of your allocation, as we've shown previously. Like, in this case, we're always we're leaving the bounds of the allocation. We're either going one element over the array or going outside of our dedicated cell. But in this case, there is no allocation to point to, and in that case, the pointer is completely invalid. There's no way that we can work with it. It doesn't make sense to use it. Now, sometimes it's actually useful for us to be able to return pointers from scopes, be they functions or blocks like this. And in this case, we do a little trick where we allocate on a different tape that lets us choose when we deallocate. So with this example, we're creating a little cell for our pointer x. Then we're going to allocate some space on the heap for an integer. So this is basically the same as creating a variable into x, but in this case we're returning a pointer to it instead of having it be an owned object. And then we need to initialize it with some value in order to use it. So we're going to initialize it to 3. In this case, I've just named our cell on the heap y so that we can name the thing that we're pointing to. In this case, once we're done using y, we've done whatever we need to do in between 2 and 3, and we've moved things out of the scope. We need to manually free this memory ourselves. So we just pass back the pointer x to the function free, and that gets rid of our cell on the heap y and invalidates our pointer. This is a very common way to allocate data that needs to be of dynamic size. So it allows you to create things like growable arrays and other cool data structures like that, where you don't necessarily want pointers to be tied to the function in which the values were created, which is very important. Dereferencing is how we get values out of a pointer. We've talked about this, but there's a couple of rules we have to follow, in the sense that assertions we have to make sure that we're upholding. So we must make sure that the pointer is not null. Null is essentially a sentinel value for the pointer, just like 0 is for integers or false is for booleans. It's a special kind of value that basically means a pointer to nothing, which can be used when we don't have a pointer. The type of the pointer and the allocation must be the same. So if we're dereferencing, say, an int pointer, but the allocation has size of short, that's going to cause some issues because we're overreaching the bounds and we're actually grabbing a greater amount of bytes than is in the allocation for short, which will cause errors. With our provenance stuff, the offset of the pointer has to be within the allocation, so that means you can't index past the end of an array, you can't index around outside of a variable, that's bad. And the allocation also has to be initialized. We have to assign it a value, as we did in this previous example. We need to actually give it a variable manually, otherwise, malloc, when we dereference x, it could actually give us any value because it's initialized. It's not set to 0 like the array set notation. Instead, it's just treated as if it wasn't initialized, which can cause issues. Now, obvious question, what if we don't do that? What if we just don't follow the rules? Which, I mean, it's a very reasonable thing to ask, obviously. Why the rules here? What happens if we break them? And the answer is undefined behavior. This is going to be the bane of your existence in C, because it's going to make debugging a huge pain. And there's a couple of reasons why you don't want it in code. To put it simply, C is really powerful and low level. And because of this, C allows us to write operations that don't necessarily make any sense. It allows us to write things that it can't generate code for, because it, like, what am I meant to do when I dereference a null pointer? I could define something for it, but checking and making guarantees around that isn't always possible. So, there's a couple of operations that this doesn't make a lot of sense of. So, obviously, reading from memory that isn't initialized, freeing a pointer twice. So, if we have an area that we've malloced and we call free on that pointer twice, freeing it the second time is going to cause some issues. Dereferencing a null pointer is the classic example. We're going to see that in a couple of the examples that are coming up. Another one is casting to an invalid type. I mentioned earlier that working with bool has some caveats. It's not just a char. It's a char with a couple of assertions about what value it can be. It has to either be a 0 or a 1. If you cast an integer 3 to a Boolean value, that's not valid. There's no meaning that has in comparisons, and you're going to run into a lot of problems. And indexing into an array out of bounds works with our provenance that we've talked about. There's also a couple of subtler cases which, in practice, could have things defined for them, but don't for optimization reasons. One is division by 0. There's no, obviously, even in math, there's no meaningful operation we can do for that. We can't represent infinity in the integers. We can in floating point, and I think that's mapped out in their semantics. So division by 0 isn't an issue for that, but otherwise in integer land, you're going to have problems. If you don't return a value from a function that returns a certain type, C has a couple of ways it can assume. It either assumes that you never return from that function, or it just goes on assuming that you have returned something and then causes more problems down the line. And also, overflowing a signed integer. I've mentioned earlier that AMD64 or x86-64 uses 2's complement integers. However, integer overflow isn't actually defined for all. It's not defined in C because we could be using a different representation like xs 2m minus 1 or signed magnitude or 1's complement, where the overflow semantics are different, and because C can't guarantee certain things about it at compile time, it explicitly forbids it. Because C can't generate code for this, the compiler makes sure that you don't write them. And by the compiler makes sure, I mean you make sure. This is very similar to preconditions on functions, like with stuff we've done in the Python course. So if you disobey the preconditions, expect that your results will go awry, except this is for the entire language. The reason why the compiler will not just error out on a lot of this stuff, there are some cases where it definitely can, but in more complex circumstances, the reason why the compiler will not just error out with something like that if it detects the contract is broken is because it can't always check. The halting problem is a big problem for static analysis and a huge pain for everyone working in the field. And so we kind of just have to trust the user not to screw up. Undefined behavior is what you get when the compiler finds an undefined operation in your code. It allows the compiler to optimize your code by removing cases that essentially can't happen. And they're impossible because we've declared that in our contract with C as a programming language. This is a pretty simple example to show how the optimizer can exploit undefined behavior, or UB, to make your function run faster and kind of simplify it in order to get rid of certain branches. In this case, by dereferencing pointer, we essentially tell the compiler, hey, I'm obeying all of the rules of dereferencing, and since one of those rules is that if I'm dereferencing a pointer, it's not null, the compiler is able to assume that the first case where we return 0 never actually happens. It's not something that occurs, and therefore it can get rid of that branch and just perform the else. And of course, with a bit of inlining to make things simpler, it just returns the dereference straight up. I like showing this example because it obviously seems like you are checking for errors, that you're checking for errors where you're not. Once you've called that dereference, you've made an assertion to the compiler that you're upholding your part of the contract, and if you're not, it's going to cause problems. If you wanted to do something like this, where you return a default value if it's null, dereference the pointer in the not null branch. So you would move that int num into the else branch instead of doing it outside. That way the compiler can't assume anything about the value of the pointer, and it still keeps in that pointer is null branch. Obviously, a lot of things that undefined behavior does is deleting your code. Compilers love to delete whole swaths of your code base because it makes your program a lot faster. Not having to call anything or knowing that some part of the program is unreachable at compile time is a really useful thing for writing fast code. In this example, we have just two external functions that I haven't actually wrote any code for, but just there as an example. In this case, at the start of the program, we assign a value to pointer, which is null. Then we call some function that halts. So that function will terminate and go back in and call the next line. Then we dereference that pointer. In that case, we've just performed an undefined operation, and the compiler is now permitted to generate undefined behavior. And since we've declared that this is something that will never happen, we're able to assume either one of two things. One is that function that halts doesn't actually halt, it loops forever, or it terminates the program in some other way, like by calling exit, which allows you to end the program with some error code without needing to return to main and return that error code there. Either way, because the compiler knows that the code will never be able to progress beyond funct that halts, because it sees any code after that as unreachable, as something that will never occur, it just deletes it. Which, even if you never used val in your code, even if like Do More Stuff never used val at all, you've made an assertion about pointer by dereferencing, you've broken that assertion, and now the compiler is allowed to delete things. Now, we can protect against this somewhat. There's linters which check our code at compile time for the few cases where that's possible, but there's also sanitizers, and these are runtime tools that essentially compile in additional error messages, so they're able to write in bounds checks on arrays, null checks on dereferencing, things like that, which will, instead of letting the optimizer delete everything, will tell you that you've hit an illegal instruction and exit your code. A couple of these are ASAN, address sanitizer, LSAN, leak sanitizer, which detects if you haven't freed a certain bit of memory. MSAN, which checks that you're not allocating overlapping bits of memory or doing weird things like that. ThreadSAN, if you're doing concurrent stuff, which probably isn't something we'll ever be doing or you'll ever need to listen to. And UBSAN, which checks for most of the undefined behavior stuff. Clang and Zig include UBSAN by default when building in debug mode. So congratulations, all of the examples that you're working with today have UBSAN built in, which is very useful to stop you from screwing up, and they're able to detect some things statically as well. Right, I'm going to quickly switch over to my editor, and we're going to do a couple of exercises where we write some actual C. You'll be able to find all of this stuff in the exercises folder. This will have function prototypes, all of that, and I think some of them have doc strings, but it also includes some tests, so we can run just grade and the name of the exercise, or grade them all. Obviously, don't try and grade them all now, otherwise you're going to have issues where they don't compile. Example solutions in the solutions folder. I wouldn't look at these yet. We're going to go through a lot of the stuff for this together, but I also encourage you to pause the video and try and figure out how to implement some of these yourself, just so that you get a little bit more learning out of it, which should be very useful for you. The first thing that we're going to write is a recursive factorial function. We can find it in this file. Very common example where we're going to write a base case and a recursive case and solve stuff from there. Okay, folks, I have opened up my code editor and run just init to set up my build directories, and we're going to write a recursive factorial function. So when dealing with recursion, we have two scenarios that we have to factor in. First is the base case, and then the recursive case. In this case, we're actually going to start with the recursive case. The value of a factorial is n times the factorial of n minus 1. This is going to be how we recurse. And now we also need to do the base case, where we want to return 1 if the number is less than or equal to 1. See my ligatures popping up just for that. In this case, we will return 1 because it is the multiplicative identity. One thing to note about the function signature is that we're using unsigned ints instead of regular ints. This just makes things easier so that we don't have to specify a precondition that n is a positive number, and it also allows us to handle the case of 0. So we're just going to now check our code. So we will run just grade factorial underscore recursive. Our code will be compiled. If this is your first time compiling your Zig code, it might take a little while to build our libraries, but as we can see, we've passed our tests with flying colors. Our next function is going to be very similar, except we're not going to be allowed to use recursion, so this is going to show off some of our features in the way of using iteration and for loop. Once again, we've got our code open up to a very similar file with the same function signature. And in this case, we need to have some sort of base value. Generally, when we're unfolding code into a tail recursive form, which is what we're essentially doing with our iteration, our default value in the base case for the recursion is going to be our accumulator in the iterative case. So we'll also just return the accumulator already, just to provide a little bit of structure as we're writing this. Now, in the case of factorial, we also need to make sure that 0 and 1 are accounted for. And we will want to early exit on those, very similar to the way that we did with our previous factorial function. In this case, for 0 and 1, I'm going to special case 1, and then we will just write our for loop that way. In this case, we know that I is at least 2. Sorry, n is at least 2. So we will start I counting from 2 just to save a couple of loop arounds. And in this case, we want to check whether I is less than or equal to n. And each time we will increment I by 1. Just like Python, we're able to use the multiply assign syntax to combine our accumulator with our element. And we can go ahead and run this as factorial iterative, which once again passes the same tests as we did before. Right, the next function we are going to write is going to be a little bit strange in the way that we implement things, because we're implementing something that is traditionally quite recursive, but using iteration. So the Fibonacci sequence requires that we keep track of the 2 previous values. Okay, so we're going to be following a very similar structure to our previous iterative function, as is the way of the Fibonacci sequence where we start with 0 and 1. We're able to simplify this by just returning n for those values, meaning that we don't have to go through the full rigmarole of computation. Now, I did say that we would have to track 2 different values, so we're going to track the previous value, which will start at 0, and the current value, which we will start at 1. For our iteration, we're also going to take the time and start at 2. And in this case, we can just make this a regular integer because we're not using I in the actual value of the return. So we can just use a regular signed integer for funsies. And we'll need to return our accumulator, which in this case is current. Now, we do want to swap current to previous at some point, but we do need to use the current value of current in this calculation. I know that sounds like nonsense, but yep. So we'll just save a copy of that value into a temporary variable, which we will assign to previous as its new value later. Finally, we will perform the actual iterative step where we add previous to current, and that concludes our code for that. We should just be able to run our tests. And again, those all pass. Okay, so the final thing that we're going to be writing is a data structure called the stack. Now, a stack is very similar to a literal stack, be that of books or of plates, where you can only add or remove an element from the top, not anywhere in between. This is going to showcase quite a few different things. We're going to be working with a struct, which essentially combines multiple variables into one big unit. Very similar to classes, except you can't dynamically declare fields. We'll also be looking at manual memory allocation using malloc and free, as we've shown previously, to allow us to create a dynamically sized allocation. We're also going to be using realloc to grow that allocation over the course of this. Now, you can't... C doesn't allow you to access fields through pointers normally. You need to dereference the pointer to access the field. When you do this on the left-hand side of an equals, this has some different semantics in terms of being able to access things without creating a clone. But for clarity, we're going to use the arrow syntax, which allows you to just access a field through a pointer to a struct. Right, now moving over to the outline file for this, there's quite a bit. We have our struct definition. This will keep track of our pointer that we get from malloc. Length is going to be the number of elements that are currently stored on the stack, and capacity is going to be the number of elements we can store in the buffer that we've allocated. So we always want length to be less than or equal to the capacity. To start off, we're going to write a constructor that we can use to make a stack with any size, but for stack new, for simplicity's sake, we're going to return a stack with capacity 0, and that edge case is going to come important later when we talk about pushing an element onto the stack. To create a stack in C, you can use set notation where you would specify something like the pointer, the length, and the capacity. But you can't do this in returns, and we want to specify these things progressively. So we're going to create a uninitialized self, and in our case, we're going to initialize all the fields one by one. The C compiler will not let you return an incomplete struct, which is very good for us. Self doesn't have any specific meaning in C, unlike in things like Python or this in Java. Self doesn't have any special meaning, it's just a regular variable. So for our pointer, we're going to want to malloc a buffer that can contain cap ints, and because that's what we're storing a pointer of, so we'll use size of int to make that cross-platform and determinate compile time, and just multiply that by capacity. It's perfectly fine to allocate 0 bytes. Malloc will still produce a pointer that's not necessarily... you can't dereference it because fundamentally the allocation doesn't exist, but it's still a pointer that can be used as an int pointer. We're going to set the length to 0 because we have no elements. We've just created this thing. And we need to track our capacity, which is the same as cap. Finally, we will just return. Next, we're going to implement our code to get rid of our stack. Now, we don't necessarily need to drop the stack. We could just let the operating system clean things up when we exit the program. But in practice, one, you want to provide your users control over the memory that their data structures allocate. And two, sometimes you might allocate a really big stack and actually want to get rid of it so that you have more space to write more things. So we're going to do this in a way that also makes the stack object really hard to screw up using, even if you use it after you call up drop. So the first thing we're going to do is free the allocation. We're using the arrow syntax to access our pointer here. And in this case, we're taking a point. The reason why we're taking a pointer to stack is because we want to mutate the object itself rather than taking a copy, which will cause some issues when you take copies of pointers and their tracking information and it's not synced with certain things and it gets weird. But we're going to be very careful and do things the right way. So in this case, we're also going to set the pointer to null. This is just going to make it really clear to anyone who's reading our code that this data structure really shouldn't be used after we drop stuff. We'll also set the length to 0 and the capacity to 0. Basically, by setting this to all Sentinel values, it doesn't stop things from going wrong, but it can make things go less wrong in conjunction with some other code. The next function is just going to be a simple Boolean conditional. Sometimes providing things like this is a good way to encapsulate APIs if you deliberately don't want your users to access the fields of a structure and just use it with certain functions. Providing something like this is very useful. So again, very simple function. We just check if length is 0, and if it is, it's empty. Now we're actually going to write pop before we do push because it's a little bit simpler. First, we need to, as we say in the function description, check if the stack is empty. We can just pass self for that. And if it is, we're going to return 0. Now, if you had a more flexible API, you could create a function that's like pop with default, where a user can pass a default value that is able to be returned if it's empty. But in this case, we're just using 0 because it's a sentinel value, and it'll work fairly well for our application. Now, from here, we're going to decrement the length. Now, this is a great line of code because it looks very esoteric, but basically what it is get the field length decremented by 1. From there, we're going to dereference our pointer at offset length. Now, this is a very... and also return it. We really should return our value so that our user can use it. This is because we're essentially putting in length -1 and we're doing the subtraction ahead of time. So even though length is still decreased, it still exists in our buffer, meaning that we have provenance over it and we're allowed to work with it. We're now going to implement push, which is the part where things get a little bit messy, and it's where we have to deal with reallocation. So we're just going to say reallocate if out of space, and we detect if it's out of space if length is equal to the capacity. Now, even though we do increment this, we only ever increment length by 1, we're actually going to just play it a little bit safe and say if length is greater than or equal to capacity. Just to show that we're taking the initiative if someone tries to futz around with fields, and it kind of protects us a little bit better. Now, we're going to do a method where we double the size of the capacity every time we need to reallocate. That way, you don't have to reallocate as often. If the bigger your data structures get, the less often you have to reallocate. In this case, we're also needing to cover the scenario where capacity equals 0, because that's a valid value. In that case, we're just going to set it to 1. Otherwise, we're going to double it, not triple it. We're mostly using powers of 2 because powers of 2 are nice on computers. Otherwise, yeah, it doesn't matter too much. You could definitely grow it by multiplying by 3 if you wanted. It's just not a very good idea. Next, we need to create a new pointer. Now, we could copy the memory ourselves, but we're not going to do that because C provides us with a function called realloc, where we can pass our pointer and a new size. In this case, it's the same way that we figured out the previous size, where we take the size of int and multiply it by our new capacity. Now, realloc is useful because sometimes operating systems will just be able to extend the size of the memory and not have to do a copy to a new buffer. If you malloc a separate buffer, the operating system will ensure that those are disjoint, meaning that it will always allocate the new number of cells and you have to do a copy. In this case, it's just a bit nicer because you don't always have to do a copy. Anyway, now that we've made sure that we have enough space, we're going to need to write our value to the position length. And this will, because we've reallocated if we're out of space, we know that length will always be strictly less than capacity. So this operation by provenance is valid and we're allowed to do it. It's a generally good process to follow through in your thoughts, just thinking about where the provenance is, where you're sitting in buffers, things like that, and that'll help you write safer code. Finally, we need to make sure that length is correct. We've just added an element, so we'll use the increment syntax to do that. That is our stack implementation. Very, very simple, very neat little thing. And we can, of course, run our tests on it. Ooh. Oh, silly me. I forgot to pass self arrow length. I'll leave that in the edit. Who cares? And there we go. We've passed all of our tests. Now, if you want to play around with these data structures a bit more, you can actually go into the testing scripts and see what I have written. All of these assertions are just talking about the various tests, so the passes or the fails. The actions are just a reference for when you're reading the tests and things go wrong. But you're just able to insert operations into here and play around with things if you want. Another thing is if you want to write your own tests or have a go at reading some actual C code, which is generally good practice, I highly recommend reading through and working with libassert, which is how I make the nice output for the tests. It's a fairly simple library. These are just strings. These compare unsigned integers. This just takes a condition to be generic over certain things. Very, very simple library, but if you're looking to practice reading through C code and writing with someone else's library, this is a good way to do that. So that's it for the presentation. If you have any questions, please feel free to fire them my way, and I will answer them as soon as I have a chance. Same thing goes for any errors with the slides. I think I've mostly checked through all of them, but some things definitely sneak through in the final cut. If you're looking to compile your own C files for projects, I highly suggest checking out the just file in the repo for all the different recipes that are run to compile your code. It's a really good way to learn by example, which I find quite useful. Yeah, and have a lovely afternoon or evening.